and I work with Julianne Del Canton, and this work is done in collaboration with a couple of other people at UW, Emily Ben Williams and Dan Weiss, who helped me with the Resolve Star side of things, and then Ben Johnson and Charlie Conway at Harvard. So to frame this talk, I think there was a lot of nice setup this morning that has made my job easy in this talk. But coming to this conference, I think that there is this tie between resolved stars and spectral integrated light studies of galaxies that thus far have not come together yet. So that's what I will try and do a little bit today. We've talked a lot about population synthesis models, and they are our way of turning light from galaxies into astrophysics, physical parameters that we want to know about the galaxies. And so the SSP, the single stellar population, is the fundamental unit for the most part of population synthesis codes, and how you add those SSPs together, whether it's a rising star formation history, a falling star formation history, bursty star formation history, that really drives a lot of the making a composite population is not easy. And that choice of star formation history, whatever form you have given it, whether it is bursty or falling, biases the properties that you derive from the spectrum. And so I've shown here the input and output mass. This is from getting the integrated photometry of a galaxy, but you see that the stellar mass is underpredicted when you use, say, a tau-based star formation history. And then this shows so the same manga galaxy, but fit with two different population synthesis codes, where you're getting systematically higher ages by 0.2 to as much as 0.4 dex. So this is, in addition to the age differences that you see, mass differences, this mass to light ratio, and the star formation that you derive is also very dependent on your choice of star formation history. Okay, and I don't think I need to impress upon many in this room that we are really in a new regime when we talk about these IMU surveys. So this shows if we were to observe M31 at a redshift of 0.5. So this is what you might observe if you were looking at galaxies from SDSS3, where the optical fiber is really covering a lot of the bulk. If we fast forward to a manga type observation of M31, you're starting to look at kiloparsec size regions within the disk. And so what I want to argue here is that when you're comparing sort of broad properties between entire galaxies across all of cosmic time, you're probably pretty robust to systematic uncertainty that are inherent in this technique. But now, when you're trying to fit for individual variations within a galaxy, you need to be really careful that you're measuring something that is not totally lost in systematic bias. And specifically in M31, we have this very rich data set of deep photometry. In that kiloparsec size region, you can see that the approximation of a smoothly varying star formation history is supposed to break down. So you have spatial clustering, temporal stochasticity of the star formation, and a very complex distribution of dust around the line of sight, all of which will alter your ability to fit the galaxy spectrum correctly. So the way that you can start to break down some of these degeneracies between star formation history and age and dust is by using resolved star populations. So I'm going to spend a bit of time on this just to sort of hit home that this is our best way in terms of absolute precision and our best way of getting temporal precision in measuring the star formation histories of galaxies. So not only do you have color and brightness information about the stars, but you have the density of points within a given location on the color magnitude diagram that gives you information about the total stellar population. And so here you can really easily pull apart where the youngest stars are versus the older stars are. And Whereas in the spectrum, you're looking at the youngest stars as they overwhelmingly dominate the integrated light. With the CMB, you have access to stars of all ages, and so you can get very precise star formation histories. So the issue with the resolved star calculations is that you only do it for a handful of galaxies that are close enough to our own so that HST can resolve the individual stars. What we have done now is we've applied for ancillary time with MANGA and gotten an observation of a nearby dwarf galaxy that has a deep enough color magnitude diagram that we can do this precise star formation history derivation, but it's also far away enough that its angular extent is consistent with the footprint of a MANGA IFU. And so the reason this is hard to do currently is that in order to get enough stars to robustly fit for the star formation history, we're going to have to add up all of the fibers within the MANGA fiber bundle. But you can see, once we do that, we can fit for things and know exactly which stars contribute to the light at that spatial location. So what does this look like? We outline where the MANGA fiber bundle lives, and we pull out the photometry from that region. We have 5-band photometry of HST on this one particular galaxy, and we run it through a program called MATCH, where we can fit for the star formation history of the population. It also fits for the metallicity as a function of time. And once you have this age versus star formation rate, you can feed that back into a population synthesis code. I use FSPS, and then you can reconstruct what the spectrum would look like given this star formation history. So this star formation history is derived with the resolved stars, but we're actually looking at what you would see if you had that star formation history with the code. Again, with the integrated light, you can sum up the spectra that fall in the same region and generate an observed spectrum. So here are the tentative results. This is a first pass where we just summed up all the spectrum of the footprint. You could imagine doing this on smaller subregions if the data allowed for it. And you can see that the star formation history reconstructed spectrum is much bluer, but funnily enough, you get actually really good agreement on the calcium triplet. But we found that this is a little bit sensitive to exactly how complete you are with your photometry, so we're still working to make sure that our artificial star tests to make sure that we're fully complete within our region are doing well. There was also some talk about the difference between light-weighted and mass-weighted properties, and I think this is something that's important to discuss in more detail. You are always fitting for the light-weighted properties when you are doing spectrum fitting, but this mass-weighted property is often the thing that has these sort of important astrophysical implications, like how is mass built over cosmic time. And so here we're looking at the cumulative star formation of this HST galaxy. You can see that 50% of the stars of the stellar mass of this galaxy are around 5 billion years old. And by generating the spectrum from the star formation history, you can see exactly how much a given population contributes in terms of overall light. And that 50% of that mass is 5% of light. So the boon of this is that we will be able to assess the biases that are introduced by chopping up during the spectral fitting process. How does your grid of SSPs affect the derivation of your star formation history interval? And so to end on a challenge, I propose this grand experiment. For all of you with population synthesis codes out there who do full spectrum fitting, this is an opportunity to set a standard between codes. I have a true or a gold standard star formation history and a spectrum, and by testing how other codes reproduce this star formation history, we can get an idea of where codes perform better or where codes perform worse. So.
Super. And we have Eric M. Selem. First question.
Hi. I can shout. Yeah. Very, very nice work, and I think you're right, we should test this on the code. One question, though, is that when you transform your CMDs into a star formation history reconstructed spectrum, this is a major step. How do you check and what are let's say, residuals that are left over when you go back to your CMD trying to use these statistically from the star formation history that you assumed?
Yes, that's an excellent question. So the code that I used, Match, was developed by Andy Dolphin, and it has two ways for dealing with error. It has both the systematic uncertainties that happen when you sort of translate in temperature and luminosity of like your isochrones into the CMD fitting process, but there also is sort of the random statistical variations that you might produce in the star formation history itself. So we can run a Monte Carlo estimate of how fluctuations in the star formation history can manifest themselves, and then I'm doing this step where, given 1,000 different star formation histories possible for this one galaxy, what kind of stochasticities in the light does that translate to?
And does this correlate with the difference you see in the observed spectrum in any way?
Yeah, so I've not done the detailed comparison between these two yet, but that will certainly be the next step.
Kevin, speak louder. Kevin Bundy is next.
I was just going to suggest to the chair that we make this one of the challenges or questions for the meeting. Let's see if we can actually address what Mel wants to do and fit some of the synthesis code.
So I'll get to work tonight.
Yeah.
Right?
I do have a follow-up question, which is can you imagine summing up different components of the manga fiber to sort of sample different parts of the galaxy? Do you have enough signal?
Yeah, so in terms of the manga spectrum, we have enough signal to add up within, so this fiber bundle is slightly offset from the center because in part I wanted to get at spatial regions with different star formation histories, and so if there's a particularly bursty star forming region over here, you can imagine seeing if the process does better when you're looking at sort of the outer regions of the galaxy. The limit here is, in here you're crowding limited for the photometry, and out here you actually get deeper, but there are not quite enough stars that qualify for that area, so I think it's actually limited by the photometry in that case.
Question to Matt Bershady.
No, this is excellent fundamental work. Someone ought to give you more time to observe M31.
I agree.
Yeah. Okay. So, the question I have about this, two. One, I'd like to hear why you think your reconstructed star formation history, why your model doesn't lead to observations. But really, more generally, it's about testing different codes. I think the real issue is one you see, if you look at your precise gold standard star formation history, if you look at the power of how much star formation occurred at 10 gigayears, and you look how much light that contributes to integrated cellular populations, does anyone in this room believe if they can discern the star formation history from integrated light between 5 and 10 billion years? And if not, then this is the only way to go.
Okay, I'll take care of this.
So maybe I can answer part of that. So I think this should be part of a larger scale endeavor. If we can observe, say, M31 or NGC 300, some galaxy that has regions that range in metallicity and AV, in star formation history, and you can imagine a number of parameters that you want to test this for, then you could construct a library where you would match star formation history from the resolved stars and the spectrum, the integrated light for the same area. You could imagine then using those as a way of calibrating, empirical calibration across all of these different parameters for fitting codes.
Now I'm going to invite Suresh to start his presentation. We have a penultimate question and finally.
So this is great work, Thank you for a really clear explanation of star formation histories. I want to just address actually one of the questions, one of the first questions. I've done exceedingly similar work that I'll be talking about tomorrow, but instead of looking at spectral galaxy, it looks at comparing what you would get from star formation history, predicting UV light and compared to the galaxy. And I've done the test with 4 different models, essentially the challenge that you suggested. Rather than doing it in a spectral analysis, I've done it in an individual waveband. And the short answer, is that in some band passes, the models do a really good job of predicting what galaxy observations show. In other band passes, particularly the far UV, which is where most star formation rates, many star formation rates are based on, the models are not doing a very good job of measurement. So some of that has already been done. And I'll talk more about it tomorrow, but I think this is a really interesting way of going about it, so it's a full spectrum.
Okay, looking forward to it. I'm giving you one more question.
Actually, by
Or,
Dr. Q, I'll take.
This is, of course, as has been said, very nice work, but just to pour a bit of water into the wine. I'm itching about gold standards. You've shown that the reconstructed spectrum does not fit measured manga data. Manga data won't go away. So the CMD reconstruction cannot be everything. It's right now it's doing something that is different, and it's not. I'm not saying it's wrong, and don't defend yourself. It's fine.
I simply actually use gold standard instead of ground truth for this exact reason. It is, in terms of precision of the time precision you can get, resolved stars are our current best way of resolving the star formation history.
I don't.
Not necessarily with this galaxy, with this. Yes.
I don't generally. CMDs have that problem.
Right, they do. Okay, thank you very much, Dan.